last time was really mostly about notation. And this time, what I really want to focus on is chapter 2, which is all about norms. Okay, now, some of you have taken advanced math courses and therefore are very familiar with norms. Some of you have only taken an undergraduate course and may not know what a norm is at all. So we're going to start pretty basic. Now, what are norms all about? Well, in the end, let's sort of see where we're going, which is actually now at the end of the chapter, but I'll probably want to move this to the front of the chapter. So, one of the topics later on in the semester is going to have to do with solving ax equals b, which is something you've seen in an undergraduate class, right? Now, the fact is that because we write a program to solve this, so a and b are given and we solve for x, what is really going on? You know, really what's going on is here you have your domain, which is a bunch of vectors, right? Typically it's Rn, actually. Well, so a, we're going to take a to be, let's make it real, and we'll make it n by n. This maps to the range or codomain, which is typically Rn as well. And what do you have? In goes b, out comes x. And the mapping there really is this right here, right? Now you then go and you implement this with some routine, magic routine. So you can think of this really as a function f of b. Now what happens when you implement this as an algorithm? Well, even though in exact arithmetic your algorithm may give the exact answer that you want, in practice round-off error happens, right? So really what happens is, let's get some color in here. So in blue, what happens is that in goes b, and out comes some f hat of b, right? And then what? Well, then we need to say, well, is this output close to that? Well, you might be able to kind of stare at it and say, well, it looks close to me, that's good enough. But really, we want to mathematically formalize what it means. Now, these outputs typically are vectors, so we need to come up with a way of answering the question, how big is a vector? And it turns out that often this change here is somehow related to how quote-unquote big the matrix is. So we have to have a way of quantifying how big a matrix is. Now, because this is a practical course rather than a mathematical course, well, there's going to be a lot of mathematics, but we always want to keep practical issues in mind, we need to come up with a way of figuring out how big it is that is of use for theoretical purposes. And we have to come up with a way of how big is it that actually is easy to compute. Because if it's hard to compute, then we may not be able to tell the user of the subroutine how big things were without an unreasonable amount of computation. So we need to come up with measures. And these measures should act sort of like length. Length you learned how to compute for a vector. That's just the Euclidean length. You take the square root of the sum of the squares. And we need to do that for vectors, and we need to do that for matrices. And that's what we're going to talk about